Right. So if you have 0 minus a negative 20, that's still 20 volts. For the electrons, for the positive charge to flow from left to right through here, this has to be a higher potential than this. If there, come afterwards, we'll talk. Are there any other questions? Wow, which way? No. They're yours. I've recorded them. Wait a second. I don't always do that. All right, where were we on Friday? We started to introduce this whole idea of magnetic fields. All right, let's put those away. Let's focus on lecture. We will need your clicker quizzes. As a review, if I have a wire and the current is moving down the wire, which direction is the magnetic field over here? It is coming straight out towards you. And over here, into the board. If I were to draw those with a... Is that coming out at you, or is that going into the board?
Coming out.
Out. You're seeing the point of the arrow. And that into the board. Gauss's law for magnetism. The net flux out of a magnetic flux out of a closed surface is 0, no matter what. All right. Perfect. Do we need to review vectors? We probably will. So, on Friday we talked about what creates magnetic fields. We said that around a moving point charge we could use Biot-Savart's law to find the magnetic field around a moving charge. And we found out that it was proportional to 1 over the distance from that charge squared, just like the 1 over r squared for a point charge, the electric field drops off. If we have a stream of charges flowing through a wire, we found out that the magnetic field dropped off as a function of 1 over r. Inside a solenoid, we found out that we have a uniform magnetic field, at least in an ideal solenoid, and the magnetic field is constant inside that solenoid. So we can calculate both the magnitude and direction of a magnetic field. Now what happens to an object moving through a magnetic field? It works out that the force is proportional to the charge that's moving through that magnetic field. It's proportional to the velocity, or the speed of that charge, and it's exerted at a right angle to the direction of its motion and of the field. So if the field is straight up, and I'm a positive charge moving in this direction, the force on me is not up, it's not forward, but it's at 90 degrees. It is going to be V cross B. Now this is very odd. The force is tangent to my motion. So it's really kind of interesting. If I'm in a uniform magnetic field, and let's say I'm moving the field straight up, and I'm moving in this direction, and the force is on me to the right, which way am I going to start to move? To the right. So I start to turn to the right. Now, which way is the force on me? It's towards the center room, so I'll continue to turn, right? Now which way is the force on me? So what am I going to do? What type of motion do I have? Circular motion. How much work is that field doing on me? 0. Am I accelerating? Yes, because I'm changing direction. So this is very much circular motion. It's very, very interesting. All right. So let us, without any proof, I will just state that mixed up my notes. That's my yesterday's notes. That the force on an object charge moving through a magnetic field is found with a cross product. The force on our body of interest will be equal to the charge times the velocity across the magnetic field.
Are either one of those cross products a unit vector?
What's that? These are not unit vectors. These are the velocity vectors and the magnetic field vector. We could, I mean, if you wanted to, remember that this could be written as Q speed times our unit vector cross B unit vector, right? Now you can do a little math and say that's equal to Q B times B hat cross B hat. Just doing vector math. Well, that seems to be a tighter, cleaner notation. You guys are getting pretty good at being able to do this. So, this begs that we review circular motion now, doesn't it? A number of people have come into the office, and I've showed them that circular motion is the same physics as linear motion, except that we have a few constraints. First of all, with circular motion, what's happening to the radius? If we describe the motion as a distance from the center of the circle, the radius never changes. So that actually helps our math. So one way of saying that the radius is constant is to say the rate of change of the constant of the radius with respect to time is 0. Any questions? So if we say our distance along the circle, s, is r times theta, the speed of the object will just be the rate of change of our position, s, with respect to time, how far we traveled, which is r d theta dt. But we know from past that d theta dt we've defined as the angular velocity omega. The reason we've done that is it's very convenient for our circular motion. And we can say, therefore, that our speed, as we move along outside of a circle, is the radius of that circle times our angular velocity. But we've done the very same math we did in linear motion. Our velocity and our speed in the x direction is the rate of change of our position in the x direction. The acceleration is the rate of change of our velocity. If I just look at its magnitude, I can take the derivative, and I find out our acceleration is r omega squared, or if we remember that omega is equal to v over r, it's equal to v squared over r. And I say no work is done by the force. Why? So if I'm moving, the force is acting on me, I'm moving, how come there's no work done?
It's staying constant from the source.
Because the force is always perpendicular to my motion. For there to be work, there has to be a component of my motion in the direction of the force. Right. The speed is constant during uniform circular motion. If the speed isn't changing, how can there be acceleration? Our direction is changing. So the velocity is a component of magnitude and direction. If either the magnitude or the direction is changing, the velocity is changing, we do have acceleration. Right. Is there anything, such thing as non-uniform circular motion? Is that possible? If we have a net torque on an object, there'll be an angular acceleration, right? So, what we're looking at is uniform circular motion, but just a reminder, there could be non-uniform. Any questions about circular motion? Right, big equation here. We're going to practice this. We'll have a bunch of practice problems. If I have a positive charge and a negative charge, both moving through the same magnetic field and they're both moving in the same direction, is the force on those two objects the same? Is the magnitude of the force the same? Is the direction the same?
No.
No. You have to remember that this has a charge. So if I have a positive charge moving through a magnetic field and the force is this direction, a negative charge moving through that field in the same point in space, going the same direction, will have a force in the opposite direction. So remember that Q does have a sign on it. So, remember the Q in front. That's the biggest mistake I see. People forget, when I have a negative charge, they forget to use the opposite direction that they get from the right hand. Keep your left hand in your pocket, or if you're going to use a negative charge, make sure this is for negative, this is for positives. Some people do that. It makes me a little nervous. But generally speaking, I think it's a good policy. When you're taking cross products, keep your left hand in your pocket. Don't. So this is the old way. You can point all your fingers or your index finger in the direction of B. Curl your finger or point your middle finger in the direction of B. And your thumb will be pointing in the direction of F or V cross B, or F for a positive charge. Force for a negative charge will be the opposite direction. Don't forget Q. I will bug you guys about that, but it will show up. It will be a problem. So I think the best thing to do now is to start practicing. We'll do practice. Get your clickers out. So let's think about this. We have a proton. What's Q? Positive. It is moving north. Decide in your mind which way north is. In a region where the magnetic field points up. So we're going to have north, south. So let's go ahead and look at north is that direction, south that direction, east, west, and then the field is up. These don't get recorded. Wednesday, I promise, we'll have a repeat of these types of questions. All right, that's 3, 2, 1, stop. Oh, I like seeing a lot like that. 83% right out of the gate. That is excellent. So, we have is moving north. The field points up, therefore, force is to the east. You guys did great, 80% first shot. I am excited. We're on a roll. Now the field's pointing north. Object's moving north. No. No left hand. Well, the real temptation is, especially when you're in a test and you're writing, you're busy with your right hand writing, so the other hand's just sitting there waiting to be used for the cross product. All right, 3, 2, 1, and there you go. We've got one with it. All right. So they're pointing in the same direction. What's the cross product of two vectors in the same direction? 0.
Can you see the answer?
Oh, that's less good. Try that.
I have a question.
Yes.
As far as that goes, I don't know. If it's pointing, I understand that it's not, if it's a cross product, but magnetic field is circular? Or is it not?
In vision, we're in a solenoid. And
Okay.
During the solenoid, we have a uniform field that's all in the same direction.
Okay, because I was thinking like, if it points north, then it also points.
Well, we don't. All we know is where we're at is pointing north. We're moving north. There might be curvature to it, but at the point we're at right now, the magnetic field is north. We're moving north. At that instant, there's no force, magnetic force on us. Now, we might move a little bit forward, and now the magnetic field has changed direction, and we're still going north, and now there's a force on us. But at this instant, where we're at, the field is north. We're moving north. We don't know if we're in a uniform field. We don't know what type of field it is. But at this point, right now, my velocity and the field are aligned. There's no force on me. An instant later, there may be force on me. The field may change direction, and I may not have the force on me. So again, we imagine north, south, east, west. The charge is moving, like an electron, it's moving upward. I saw his left hand sneak its way into his pocket.
Or pull out. So it's negative charge?
Oh yes, I wasn't going to tell you. It's an electron, guys. What's Q? Never
Negative.
forget Q.
-%.
Yes. The charge. Thanks, Ed. 3, 2, 1. Alright. Remember, it's a negative charge. So, when you find the force with the cross product, you need to go, the direction of the force is the opposite direction. Alright, let's see how we did.
What do you change it?
You're still counting?
Let's practice.
See.
We're still at 2/3 of the people. Alright, so the electron's moving north. The electron is moving up. The field is
North.
to the north. So my thumb's pointing west. So if this were a positive charge, the force would be to the west. But since it's a negative charge, it's to the east.
It's negative, so
So you can't use the left hand?
You can use the left hand.
If it's not.
But I discourage you doing that, all right? I'm not even gonna show you.
Okay, now I have a question. You said you don't have to point out.
So
You're pointing up.
I'm pointing up. That's the velocity. The field is pointing north.
Yeah, so your fingers are pointing.
My thumb is pointing to the west.
Wait, I thought you said your nose was just pointing south.
No. You point.
Rotate your hand.
Okay. Take your index finger, your pointing finger, point that in the direction of the velocity. That's up.
All right.
Then you take the rest of your fingers, put them at a 90-degree angle, and point them to the direction of the magnetic field, which is to the north. And which direction does your thumb point? It points that way. So if this were a positive charge moving up, then the force would be to the west. But it's negative, so the force is in the opposite direction, to the east. Other questions?
I get this right.
I promise we're going to have this quiz. I promise this cross product thing is going to be very key to our grades in this section. So we're going to hit it because we need to learn it. And it's valuable. All right, now, the positive charge here tells us it is a positive charge. Right? I'll typically make it the x this way if it's moving that way. So our charge is moving that way. It's moving up on the paper, and our blue magnetic field is moving to the right.
It's moving.
I think we need to.
You want to
You
open
want
up?
to open up the?
Oh, I will open that up. Thank you.
Okay, so the charge is moving. The velocity is moving into the screen? Or is it moving up?
It's really entertaining watching this kind of test.
You should.
Videotape.
You should just videotape people as well.
Well, it's probably sometimes people start to get really hard things. Yeah.
Yes, your tests are
All
hard.
right, 3.
He's like mine.
I just don't want to have anyone like sprain their elbow. I sprained my elbow during a physics exam. That would just sound bad. 3, 2, 1. Come on, there's 2 more. Have an opinion.
Right, left.
All right. So we have. Let's go ahead and get our answer. We are moving
What?
up. Magnetic field is moving to the right. It's a positive charge, so the force is into the screen. Yes,
Yeah.
that's getting better.
Those are all moving in this way. The velocity, so it's like that.
Alright. So which way is the magnetic field going? What are you seeing?
Towards
You're
us.
seeing the points of those vectors. Is that a positive or negative charge?
Positive.
I think 2 people.
3, 2, 1, and done. Alright, V is up. The field is out towards you. The force is to the right. Oh, come on. I'm gonna do it.
We're moving in the wrong direction, guys.
Oh.
Okay. So,
Oh, I did something trickier this time. So, I forgot what type of charge this is.
Come on.
Actually, do you guys do they do cloud chambers in physics 3? So,
Physics 3.
tell me what a cloud chamber is.
Okay, so the cloud chamber is, I believe it's dry ice, and you can see particle decays because I think it's do they ionize things? Or it's the magnetic field of the Earth makes ions go in little circles. And it's really fun, and you can sit there and watch it. That's a whole lab in nuclear physics, is just sitting there watching this happen. It's
And they
great.
curl one way or the other. And you don't know what charge they are, but by knowing the direction of the magnetic field, you can figure it out. Right?
Sounds dreadful.
Oh, it's so cool.
Oh, man.
Sounds dreadful.
We do have a difference of opinion on how cool this is.
I think it's really cool.
Some people with the
Oh, man.
All right.
I think I'm learning
Yeah.
slowly more than stuff out of books. It's how
I wanna watch it.
People like weird things in college.
3,
Taking temperatures.
2, 1,
Figure out how to
and
calculate.
all right. If this was a positive charge, the velocity would be to the left, the field would be down, and the force would be out towards us. Is the force out towards us?
No.
No, it's into the screen. Therefore, it must be a
Negative.
negative charge on the left hand.
Charge your left hand.
Let's see how we did.
No way.
Not bad. Not bad.
We did this crazy concert last night. It's close.
What is the charge?
80 seconds. What is this?
All right.
Oh, we gotta go.
This is
You just the other way to do it.
Oh, thank you.
Oh, boy.
Did it get you? I just started.
Oh, he's
With B's going that way, F's going that way. B is coming. Are you seeing the points or deflection?
You can't.
Points. Going out at you.
Carpal tunnels. Carpal tunnel from physics.
Another left hand. Three.
Oh, joke's on you.
No. One.
I got it.
And 2 more. There we go. It's the third shot. Alright, so V is down that direction. B is out towards you. So if this were a positive charge, F would be this way. So once again, we have a negative charge.
Shoot.
Screw you, look at that.
Ah, 91. That's our best yet.
Could have been bad. Alright.
Oh, I'm sorry, open start. Three,
I don't know if it's true.
2, 1, and
Uh-oh.
oh, did I? We're going to assume this is actually. So when we come into at this point here, which direction is the force on the particle?
Doesn't matter.
To the left. So there's V, and the force is that way. It's a positive charge, so that implies that V must be into the board. Let's check up here. We now have V. The force must be this direction. So again, V's there. Now, just as a side note, If I put a charged particle right here in the corner, say a negative charge, wouldn't the force look the same? If I put a negative charge here, wouldn't the force be towards the negative charge the whole way?
Yeah.
And wouldn't we get very similar motion? Just something to keep in the back of your mind for the future.
I'm confused. Were you wanting the inside of the box or the outside of the box?
Yeah, because
Yeah.
outside of the box anyway, we sure.
Oh,
Yeah.
I lied to you, didn't I? All right, so I was talking about the inside of the box, but it says the outside of the box. So, inside, outside the box, I just lost 5 points. Outside the box, which direction is the force on the particle? It's, if anything, it's this way or this way. We can't be sure, but we look up here. Is there any force this way or this way? No. So, there's no force outside the box. So the field outside the box is
0.
Now, if I only had this part of the field, or only had this part, I couldn't be sure because the field could be in this direction or in this direction. James.
So the index finger is the velocity of a parcel.
For the cross product, the index finger is the first vector, in this case the B. The other fingers are the second vector, in this case B. And the thumb is the cross product. Okay. So I lost 5 points. Let's see if you guys do better than me.
Just out of curiosity,
We'll get to that next. What's it?
like since the right answer is it's 0, but if it pointed to the left, wouldn't that make it 0 anyway?
If it pointed to the left, there would be 0 force on this one, but there would be force on its motion down here. Right. So that's why this one that showed the motion here and here.
So if it just showed the end point, or the end spot, then it wouldn't have.
Right. Because if I said that it's moving in this direction and it's not accelerating, there's no force on it, does that mean there's no magnetic field? So I have the positive charge moving straight up, there's no magnetic force on it. Does that mean that the magnetic field is necessarily 0?
No.
No, the magnetic field could be oriented in the direction of the path. Alright, let's see if you guys, how many beat me?
Nope.
Nope. Oh, it looks like almost half of you beat me. Alright, now, let's look inside the box.
Oh, weird.
Alright, real
Can you
quick.
start it?
Alright, 3, 2, 1.
Wait,
Open.
that's what he was
I kind of told you the answer to this one. So. If we look at 100%, that makes people look listen. Convince yourself it's true, though. 3, 2, 1. Alright, alright. So, if it's moved.
I clicked the wrong one. No, I meant to push that, I promise.
Alright, so the force, I can see. The force is, does everyone see that the force has to be towards the center? It's a positive charge. Therefore, the force is to the center, the velocity is in the direction of motion, and in all instances inside the box, the magnetic field is down. Joshua?
Two of those answers would be true though, because as you mentioned, if we put a negative electron, well, not a negative, if we put an electron in the corner.
If the electron had the right charge, the motion in here would look the same.
So couldn't the magnetic field be 0, theoretically?
Yes, it's implied that there's only a magnetic field. I mean, there could be a huge mass in the corner too, right?
There could be. Oh, wait, Joe said we should just results.
What's that?
He already did.
Yeah.
Oh boy.
Yeah, I know, that's what I mean.
Well,
Proton also.
we don't know that they're going the same velocity, right?
That's true.
We know the electron has a smaller mass. But this could be a really slow proton and a really fast. Let's work this together. How on earth would we figure it out? Charles, how do you figure it? With either of these particles, you have some radius of curvature. We have some Q. Right? Traveling at some velocity. What's the free body diagram look like? Let's look at the top. We have some acceleration downwards, don't we? It's the same direction as the F magnetic. Let's let this be our y direction. We sum our forces in the y direction, what do we get? It's going to be Q, B, B. Right? And what does that equal? Equals M times A. And what is A equal to in this case? B squared over R. Can we divide both sides by B? Multiply both sides by R. And we get Q B times R equals M times B equal to P. So what does this tell us? It tells us for a given charge in magnetic field that the radius is proportional to the momentum. Those two, which has a larger radius, the proton or the electron? The proton, so that would tend to tell us what? Proton has a larger. And I'm not going to score that one because that's. So the hint is that momentum is mass times velocity. Proton is. That ties in our circular motion. It gives you a sense of where we're going with this stuff. Alright. So where do magnetic dipoles come from? Again, we talk about magnetic field around a loop. We wrap that wire in a loop. We have current circulating in loops or rotating charged bodies. Then we get magnetic fields. So if we think of electrons orbiting in a nucleus, that would give us some sense of where a magnetic field comes from. We think of electrons as having spin. That's probably a little more accurate idea of where that magnetic field comes from. The bottom line is we have rotating charges at an atomic level that create magnetic fields. Okay. I haven't showed you this yet. Now, let's go back to here. If I told you that we had these rotating magnetic fields like this, and I took the wire out, it would kind of give the idea there must be charged body flowing through the center of all those magnetic loops. Just like in Gauss's law where we said the net flux going out from a region tells you the net charge inside. If we make a path around a loop and we measure the magnetic field all the way, so I say how much magnetic field in this direction, and I sum those up. It's called a line integral. At each little increment of space, we'll say, how much magnetic field is in the direction I'm going? And we add that up. We find that loop integral, that line integral around that loop. If there's a net magnetic field as we go around in that circle, that implies that there's some current. Now if I go to a region of space and I were to make a loop like this, notice when I'm going in this direction, the magnetic field's going in the same direction I'm going, and I jump up to here, I'm going to tangent the magnetic field so there's no value. Then I move back the other way. Now I'm moving against the magnetic field. If I were to sum the strength of the magnetic field times each of those little lengths of distance around this loop, I end up with 0. Because there's no current going through that region right there. That whole sense, mathematically, is expressed as Ampere's law. And it looks really ugly. But what it's saying is if I walk in a path around some place and I measure the magnetic field strength here times the distance as I travel, and I do this in little teeny chunks, and go all the way around the path, and when I add it up, if I get 0, that means there's 0 current going through that area. I've just cut the compass. If I get a positive value, it means that there's current going through. If you wrap your fingers in the direction I walk around the loop, there's current going through in that direction. If I get a negative value, it tells me the current's going through in the opposite direction. V is the magnetic field, mu is the permeability constant, and I is the current that we close when we wrap around in our loop. And we'll expand on that. What's that? We'll do examples here. Right now, what I want you to think about is if I know I know this integral divided by mu. Or if I know that integral and I divide by mu.